Hi, welcome back to our lecture on a practical guide to quantitative finance interviews. Today, we are going to talk about Brownian motion and stochastic calculus. So Brownian motion is a quite classic way to describe the movements of a certain particle in the physics world. But now we want the intention we want to introduce it here is that because it's a foundation of the whole stochastic calculus, and also where we can start from to derive the Black-Scholes-Moulton model. So what is Brownian motion? A Brownian motion is actually a continuous stochastic process WT. Before, when we talk about Markov chain and martingale, we're all talking about discrete times, which means we can divide time into one dot, the second dot, the third dot, just we can count the time points. But in real days, the time is continuous, right? Everything is happening continuously. So we want some kind of stochastic process to describe a process like that. And that's Brownian motion. We call it WT, and sometimes we also call it BT, denote like that. And there are lots of properties of a Brownian motion. And interestingly, part of the definition, such as W0 equal to 0, and some properties are actually so obvious that we often fail to recite all the details. But I'm going to go all of that through for you. So the first one, please remember, we actually do have an initial point. W0 will always be equal to 0, which means at the very beginning, we are starting from our initial point where nothing is increased or decreased, okay? And the second, increments of the process, which means at any time when we take any difference of some non-overlap period during this process, for example, T1 minus 0 and T2 minus T1. But please note that T2, T1 has a strictly statistical order that makes each increment has no overlapped part, okay? And after that, all these increments are independent, okay? And the third bullet point is that each of these increments is normally distributed with a distribution where the mean is always 0, while the variance is determined by the gap between the two separation points, which is just the distance between Ti plus 1 and Ti. And this is going to be the variance. So if you want the standard error, you need to take the square root, okay? And these are three the most fundamental properties, but there are also some following things I think you should remember. The first thing is that the expectation of a Brownian motion is going to be equal to 0, because as we see here, the mean for any increment should always be 0. And we have W0 to 0, so basically WTI minus W0 should also follow something like 0 with a mean 0, right? And also its second moment, WT squared, is actually T. We can prove that by using variance minus the square of the mean of WT, which is just 0. And all these things, we call it expectation property. And the second thing is we call it martingale property, which means it shares similar characteristic as a martingale. Oh, sorry, this is the, okay. So we have the expectation of WT plus an extra period S conditional WT is going to be the same as WT, okay? And also we have the covariance of WS and WT is also going to be S because we have the extra item. The covariance between WT and WT is going to be 0, okay? So these two are corresponding. And there are also two other important martingales I hope you should remember, and we are going to apply these two equations during our solution for the questions later. So the first one is that we can define a YT, which is going to a Brownian motion square, WT square, and minus the T. And this is going to be a martingale. Please remember this. Why it is useful? Because it actually helps us to link a Brownian motion kind of stochastic process with what? With stopping time, right? Because we have a t here, so which means when we take expectation, we can take out ET. We know that the stop, when we apply in the stopping room, the stopping time of a martingale is also a martingale, right? And the second one, we call it CT, which is the expectation of lambda WT minus 1/2 lambda square T. And where lambda is just a constant and WT is a Brownian motion. And this is called the exponential martingale. It is also just a martingale, but it has a fancy name, okay? Because it follows actually an exponential family format if you have learned that in your inference courses. And we have listed it here, and I want to show you the proof for the second part. For the first part, since it is going to apply the Ito's lemma, we are going to talk about that in our next lecture. But for the second one, I want to show you a quite elegant proof. That's to prove it is a martingale. We just need to show that ZT plus S expectation is going to be the same as ZT, right? Then it should be the same as martingale. So by how to prove that? First, we can take out the T plus S part, which is exponential of lambda WT plus WS. Why we can separate the WT plus S into this? Because using the second property, we know all the increments are independent. So this is T, right? This is WT. We can say it is WT minus 0. And this is actually what? This is S plus T minus WT, right? And we know these two are independent. So basically, we can separate out WS. And by doing that, we have the second part, which is just 1/2 lambda square T plus S. And let's rearrange the sequence where we could have the exponential part lambda WT minus 1/2 square root T, right? Which is just the ZT. And this part here has no expectation. And also the exponential of negative 1/2 lambda square S. And with the what? With the expectation of exponential lambda WS, right? So we already know this part is just ZT. Okay, and so we need to solve this part. So exponential lambda WS. I'm going to say that this thing is going to be the same as exponential 1/2 lambda square S. And can you believe that? You may ask why. Remember when we talk about the moment generation function, we said another application of the moment generation function is that sometimes if it follows a certain format for the moment generation function of a certain distribution, for example, Gaussian distribution, then we can directly apply it to change it into another format to cancel out the exponential sign. So we want to remove this exponential sign, this expectation sign, right? And this is actually what? This is exactly ETX, which is the format of moment generation function, right? We have the T here, and this is the X, which follows a normal distribution, right? So that we can just convert all this whole total part into its moment generation function, which is just exponential 1/2 square lambda square multiplied by S. And we can see this part actually cancels out with this part. So we prove this thing is equal to ZT, right? Because we only have this ZT left. And thus, this ZT is a martingale. Okay, I think it is a quite nice proof by applying the format and the shape of moment generation function, which is quite good. I hope you should remember that. And now let's go to the next property. What is the correlation of a Brownian motion and also Brownian motion square? Well, the solution to this problem is actually surprisingly simple. So at time t, we have bt. This time let's using a different denotation. We know we have either wt or we can call it bt. Either way, it's a Brownian motion. Okay. Because during the interview, you never know what's the preference of the interviewer. So I hope you get used to both of that. So we know BT is going to follow a normal distribution of 0t. So by symmetry, we are going to have EBT is going to be 0, and EBT3 is going to be EBT squared multiplied by EBT, right? Which is also 0. And applying the equation for covariance, we know that covariance xy is going to be expected value of xy minus ex ey, and thus the covariance bt squared, bt is going to be 0, because this is just the ebt to the cube, and we also have the bt is 0, so in total it is also 0. And the correlation of a Brownian motion and its square is 0. Okay. And next question. What is the probability that B1 larger than 0 and B2 smaller than 0 if BT is a Brownian motion? So let's first do the standard solution. Okay. So let's do the solution 1. Solution 1. We know that B1 follows N01, while B2 minus B1, which is independent of B1, will also follows what? N01, right? And if B1 equal to something x, which is larger than 0, and then for B2 smaller than 0, we have B2 minus B1 must be smaller than what? Smaller than negative x, right? So probability B1 larger than 0, B2 smaller than 0 is going to be the same as probability B1 larger than 0 and B2 minus B1 smaller than negative B1, right? We intentionally to construct it in this way because we know this thing, if we denote it by y, it also follows a 0, 1 normal distribution. And we just need to take the integration of all these two things, which is just from 0 to infinity. And the second thing is from negative infinity to negative x. We are going to have 1 over 2 pi exponential negative x squared plus y squared divided by 2 dx dy. And by using the polar intersection, we can easily convert this into what? 0 to infinity, and this is just 2 over 3 pi, and this is 7 over 4 pi, and this is 1 over 2 pi e r squared divided by 2, and this is r, and dr d theta, right? And we can know this is just equal to 2 pi 7 over 4 pi minus 3 over 2 pi multiplied by this negative e squared divided by 2, 0, and sigma. So by solving that, we can first we take the integration of the theta, and then we take the integration of the r part, which is just the negative, and we can have this thing is just going to be 1, and this is cancel out all the pi here, and we are going to have equal to 1/8. Okay, so some of you may ask why we can convert from here, right, all the way to from 3/2 pi to 7/4 pi. So remember, by the polar integration, we are just trying to using this theta here, and if we have our r, and we're denoting this as x, and this is y, and we know that the y should be smaller than -x. So if we're trying to find the range on a unit circle, and this is the range for that, okay? So that's it for the standard solution, but I want to provide another solution which fully take advantage of the fact that B1 and B2 minus B1 are two independent N01, okay? So we just need to use the conditional probability. Let's write it here. So solution 2, which is also a solution I like, is that probability B1 plus 0, B2 minus 0 is gonna to be just probability B1 plus 0 multiplied by probability B2 minus B1 smaller than 0, and also conditional probability B2 minus B1 larger than B1, right, by taking the absolute value. And we know this is 1/2. And this is also 1/2. And how about this? This one is also 1/2. And this is just 1/8. Why this is 1/2? Because the chance that for one thing, it is larger, we can just convert it out to have B2 larger than 2B1. We just need to discuss all the scenarios. Or you can just simply draw a line, okay? You can simply draw a line. And you can find the chance is actually 1/2. And you can actually see this thing from the plot here, because we have the B1 minus B2, which is just our y, and it need to be larger than B1, right? So we have one line here, which is absolute value of this part. And also it needs to be larger than absolute value of B1. So we just have in total this part and this part, which is just 1/2, okay? And now for the next question, the stopping time or the first passenger time problem. So the first question here is that what's the mean of the stopping time for a Brownian motion to reach either -1 or 1? So now, as we just discussed, we know the reason we have this thing is that it linkage with the it linked martingale and the Brownian motion with the stopping time. Okay, so now we are going to use this format. We know BT square minus T is going to be a martingale. And then let's T is the stopping time, which is just the minimum T BT equal to 1 or -1. Then this T is defined as the stopping time, right? Please remember, even during continuous time and space, the following property is actually can still apply. A martingale stops at the stopping time is also a martingale. So we can have expectation of BT square minus T is going to be the same as B0 square minus 0, which is just what? We know a Brownian motion's initial point is 0, so this is just 0. And the probability for BT to hit either 1 or -1 is that BT square expectation of BT square. So by this, we can have what? We can have expected BT square equal to expectation T, right? Then we have expectation t should equal to this thing, which we have the bt square for 1 or -1. It is all 1, then it is equal to 1. Okay, quite easy to solve this problem by applying the bt square minus t martingale property. Okay, now let's go to the next one. The next one, again, we are going to see our old friend, which is the reflection principle. I have drawn a picture here. You can see starting from tau t, which is just the time point here. And during this period, if we have some kind of process above this x, we can have its same reflection below the x, okay? And the question is that if WT is a standard linear process, which is just a Brownian process, okay, just another name. And tau t, x larger than 0, should be the first passenger time to level x. And what's the probability density function of tau x, and what is the expected value of tau x? So how can we solve that? Because it is trying to ask us to first find a PDF, right? So we need to find its distribution, which means we need to find probability tau t smaller than or equal to t. But we also need to consider the x, because we know that tau t is the minimum of t and wt equal to x, which means we also need to have wt larger than x. We need to consider these two cases differently. So we have, this is the first one, this is the second one, tau t, okay, smaller than t, and wt smaller than or equal to x. We need to consider these two both, right? But by symmetry. So if we have one probability that wt could be larger than x, then we can have another thing that the wt is also smaller than x, okay? So we are going to have both passes here, and these two are the same. So we can just denote what? Probability tau x smaller than t is going to be 2 probability tau x smaller than t and wt larger than or equal to x, which is just what? 2 probability wt larger than x. Because if wt is already larger than x, then its tau t should be always smaller than t, right? Because by the intersection point, if wt is above this line and we're starting from 0, there must be some point that this tau t has been there, okay? So it suddenly becomes 2 multiplied by x to infinity, 1 over 2 square root 2 pi t, and e negative w squared divided by 2t, and dw. And it's just a normal distribution. And for this kind of question, how can we solve that? Well, we simply need to denote this v equal to w square root t, so that we are going to have e negative w squared over 2t is going to be e negative v squared over 2, which is a format of normal distribution. And this is just becomes 2. And since we are from x, we have w equal to v square root t, then this is just x divided by square root t to the infinity, and a standard normal distribution 2 pi, and e negative v squared divided by 2. Okay. and this is becomes dv. Why this t is gone? Because we are going to take this square root t out when we're changing from dw dt to dv. We need to have dw equal to square root t and dv, right? So this t is actually here, okay? When we're changing from dw to dv. And for this, it is easier for us to solve. It is just the 2 multiplied by the normal distribution of x over square root t, right? 2, 1 minus this thing. This means the value for the corresponding normal distribution value for this point, at this point, okay? And we are going to also have the derivative by taking this thing, taking the derivative according to t, okay? And for part, and it, sorry, it's my theory. So I'm going to close that. And now we can see from part A, it's already easy for us to show that the expected stopping time to reach either alpha or negative beta still follows the same pattern while we introduced before. So from this part, that expected time to reach this is again alpha multiplied by beta if we are either reach at alpha or negative beta, okay? So then what is the expected value of tau x? For this question, the expected value of tau x, the stopping time, is either stopping at the is either stopping at x or what? Or negative infinity, right? So expected tau is just equal to x multiplied by infinity, which is infinity. So although we have the probability for tau to smaller than infinity is equal to 1, but the expected value of tau is still infinity. That's quite interesting, right? Please notice that. So still, even though we have proved here that the probability tau x smaller than equal to 0 should be something 2 minus 2n x divided by square root of infinity, which is also infinity. So this is going to be around 1 over 2. So this is 1. So we have this is equal to 1, but the expected value is still infinity, which means the probability for it to reach there is definitely sure. It's certain that it is going to reach to this point. But the expected time it takes is infinity. That's the difference, the main difference between a discrete time process and a continuous stochastic process. Okay, I think it's a good illustration for the difference between these two by this question. So now let's go to the next one. Suppose that x is a Brownian motion with no drift. So what is drift? You know, actually Brownian motion can be written as something like dxt. We can write dxt as equal to some beta tx dt plus some gamma tx dw. So this part, we call it drift, okay? It's something like 平移 to moving it upward or downward by some value. And this is diffusion because it is related with the Brownian motion itself, but this is just related with the time. And we can actually have a equation which is called Feynman-Kac equation, where if we denote a vtx, which is just some function of t and x, this means is going to be the expected value of a function f xt, which is just any function of x related to its stopping time, okay? And conditional on xt equal to x, then we are going to say this vtx is a martingale process. And it actually satisfies the stopping condition that VTX is going to be Fx. Which means if there is a function which looks quite similar with the function of x at its stopping time's expectation value, then we can set this Vx at the stopping time to have the terminate condition Fx. And we can also find the first derivative v plus, okay. So, okay, let's write it in this way. So we can also have the dv dt plus this beta tx dv ds plus 1/2 gamma square tx, and the second derivative of s is going to be 0. I know this may sound a little bit confusing for you, but we are going to illustrate why it looks in this format when we talk about Ito's lemma, okay? All these three is going to be related with Ito's lemma. But now for this question, we currently just need to apply that. We're asking what's the probability that x hit 3 before hitting -5. So if it has no drift, if it starts from 0 and has no drift, which means this beta is just 0, okay? Then we know it's a martingale. Then a martingale stopped at the stopping time is still a martingale. So we can just have what? We can simply have using the property alpha plus beta, where alpha equal to 3 and beta equal to 5. And this is going to be beta. So the probability is just 5/8. Okay. But if it has a drift, then it is no longer a martingale. Then we can only solve it by the property. But again, although x is no longer a martingale process, it is still a Markov process, which means probability Tx is going to be Px. The T is independent, okay? And then by using the equation I just illustrated, we can denote this Ptx as Vtx. And we know beta Tx is just n if we have a drift item n, okay? But this item is still 1, right? So we can simply find this mpxx, and we know it is independent of t, so this part is going to be 0, and plus 1/2, and this is just 1. So it is just 1/2, and pxxx, which means the second derivative is going to be 0 for -5 smaller than x smaller than 3. And we also have a boundary condition where P3 is going to be 1, and P -5 is going to be 0, which is just a classical way to define a martingale where we want x hits 3 before hitting -5, okay? And so this is just a homogeneous linear differential equation. I hope you still remember that. Y has a root R1 equal to 0, and R2 is going to be -2n, because we can simply denote this as 1/2 square root plus mx equal to 0. Okay, so 1, so it means x 1/2 x plus m equal to 0. Okay, so it has two characteristic root, and then apply the boundary. So we can have the general solution where px is going to be c1 e0x, which is just plus c2 e -2 mx, which is equal to c1 plus c2 e2 mx. And now we're applying the boundary case into that to solve out c1 and c2, which can give us c1 is going to be e -6m minus e 10m. It looks quite complex, and negative e 10m, and c2 is just what? E -6m minus e 10m over 1. And by solving that, we can actually have p0 at the initial point, right? What's the probability at the initial point? It's just equal to C1 plus C2, and we just need to sum these two guys together, okay? And another simple approach, take of the exponential martingale, is that we can just use WT equal to, we define a WT, which is just XT minus MT. So it is a martingale again, right? And we know it is a Brownian motion, and we can using exponential expectation of exponential lambda x minus mt minus 1/2 square t equal to 1, right? And we can just simply set lambda equal to -2m. And what can we find? Let's erase this part. And then if we intend, because lambda can be any constant, so if we intentionally put lambda equal to -2m, then we can actually find expectation of exponential -2mx is gonna to be 1. And we know again, a martingale stopped at a stopping time is still a martingale. So we have P3 if we exponential to n multiplied by 3 plus 1 minus P3, well, it is going to be stopping at -5, right? Exponential to -2m multiplied by -5 is going to be 1. So we can also solve out this part, okay? This is another way to apply in the second formula. And that's why I told you that all these two equations at the very beginning, these two, you should remember it really well. Because for the first time, it is related with the stopping time itself, and for the second time, we can intentionally construct some kind of martingale Brownian motion process where we can set a certain lambda to help us to solve certain question out. Because by setting certain lambda, we can cancel all the items related with t, right? We can cancel out all the items related with t to leave only x and using the stopping time, because the stopping time is related with the value of the x. Okay, so now the last question. Since x is a generalized linear distribution, well, it is going to be dt plus dw. So we have beta equal to 1 and the gamma function is also 1 by the written here. So this is 1. This drift item is 1 and the diffusion item is also 1. It is a general linear process. So you can now see the difference between linear process and the Brownian motion process. So if it is a standardized case for linear process, then it's a Brownian motion. But linear process is a more generalized thing. It can have diffusion and also drift item. Of course, WT itself should be a Brownian motion. Okay. So WT is just where the drift item equal to 0 and the sigma item equal to 1. Okay. So what's the probability that x ever reaches -1? Again, we can using the equation what? Expectation of exponential to -2mx equal to 1, where in our example, m equal to 1, right? Please remember this equation. It is quite useful to solving a lot of questions. And then we can have exponential -2x equal to 1. Then it may not be obvious since we only have one apparent boundary, -1. So to apply in a stopping time, we also need a corresponding positive boundary. But from the previous question, I think, let's see, from this question, we can already see if we only have one side's boundary, we can just set another side as -infinity or positive infinity. For example, in the question B, we have x larger than 0, which means we have the positive boundary. Then we just need to set the negative boundary as -infinity. Then for similarly, for this question, we simply need to do what? We can say the boundary is -1 and also positive infinity. And it suddenly becomes quite obvious because we just need to see the probability x average is -1 is p -1 multiplied by exponential to -2 multiplied by -1. Since a martingale, again, stopping at the stopping time is still a martingale, okay? And plus 1 minus probability -1, right? This is the probability at average is -1. Exponential -2 multiplied by positive infinity is gonna to be 1, this value. And we know this is exponential 2, and this is the probability with 1. This is just 1 minus the probability. And this thing is close to 0, so we can cancel this out. So we have this equal to 1, so the probability -1 equal to what? Equal to E -2. Okay, quite easy to solve that. And I think that's all for today's lecture. I hope you enjoy it. This is the first time we're talking about Brownian motion. Next time we're going to be talking about Ito's lemma, which is going to deepen your understanding of this whole stochastic calculus. So see you next time. Thank you.